In this video, I'm going to be going through the 2019 HSC exam. I have already had a glance through the answers. I mean, I looked at this 2 years ago when the test came out, but I had a look at the answers. I am not going to go through everything. I'm just going to give the answers because I trust your ability to read. The first question is, I haven't written out any answers for things, but I have got a couple of things ready. Mostly we're just going to be looking at the HSC solution, like the solutions they've provided. Okay, so the first thing is most students knew that a black box is commonly used in flight data. The next question is about plastics, and most students know that plastics are generally considered to be flexible, and formability means they can be made into a variety of shapes using a variety of technologies. Typically we use injection molding, but there are lots of things. Resistance to abrasion is hardness, and plastics don't have a good hardness compared to metals or ceramics. The next we have an AND gate, and most people got the AND gate. AND gate needs both to be on. That is in our formula sheet. Where am I? Formula sheet. We can see and they need to both be, we can recognize, I mean, they have labeled it as and, but they're both on, and when they're both on, we have high voltage. The only real trick here is knowing that the 5 voltage represents high electricity, and that is what we're using. So here we have a bolt. Now, once upon a time, I used to say to people, just learn the diagram on page 64 on the day of the exam. These days, I find that most students do remember head at 7, nut at 8. And so what that means is that the head of the bolt is 0.7 or 70% of the major diameter of the bolt. This is the major diameter. So if I told you that the 7 millimeters was 70%, most people are able to figure out that the major diameter should be 10 millimeters. And that's the number when we write M10 bolt, that's what we're talking about. Okay, this question here is using CAD terminologies. This is referring to, so I know that these terms are all used in AutoCAD. I only know how to use AutoCAD. I used Bentley's MicroStation or 20 years ago. And whether or not people are familiar with these terminology, well, I can tell you that if you guessed randomly, you would have done better than the state on this question. So don't feel bad if you didn't know the answer to this one, but the answer is offset. In one of my videos on Introduction to AutoCAD, I do talk about all 4 of those terms. Okay, most people should be familiar. When we see diodes, we know that diodes are used to rectify, which is to convert AC to DC. This is a full bridge rectifier, and Electroboom has a thing that that's kind of his shtick. Is there's like a mega cut of just him saying full bridge rectifier lots and lots of times, and just a cut of that. You can buy a t-shirt, which is, it's not a purely single diode rectifier. Hey, look, someone's got that's pretty cool. A tattoo of a full bridge rectifier. Anyway, the output of that is full wave rectification. You should be familiar with that. That is accessible. You should know the difference between half wave and full wave rectification. And let's get back to the paper. Okay, so this question, I got to say, I was a little bit excited when I saw a box. I just want to go straight into the phony friction formula, and that's where diagrams do help. This is sitting on a, because I saw a horizontal surface, I thought it was phony friction, but actually we're going to tilt the surface to 28 degrees. What we're going to do is we're going to use the formula sheet, and you should also know smoothing as well. Anyway. The formula sheet, we have this formula here, mu equals tan phi. So if we plug in tan to the inverse of pi, or arctan is probably the term I think is probably more appropriate, we get C is the answer there. 7 is C. And most people got that. Okay, so next one we have is which table shows routine maintenance. So if we were using cube, we'd say this is identify, circling the word identify. Routine maintenance is and commercial airline. So we're not talking about the design of or working for an aircraft manufacturer. So that the first 2 columns relate to manufacture rather than maintenance. So that rules them out and means A is the correct answer. Okay, 9, we have a beam shown, it's a post-tension beam showing steel in the bottom. Now, if we go to, I did have a picture, but maybe it's in this one. Okay, if we show beams under load, we can see in this situation, this is a typical beam that what we see is a load being applied and two reactions pushing up on either side. That's a very common, that's typically what we see in the HSE. What that does is it creates an area of compression on the top and tension on the bottom. We expect you to know that. We can see that if we're talking about continuous beams, we can see we have tension, tension, tension. So it goes from top, bottom, top. We don't expect you to know that. Cantilevers, we do expect you to know about. So we do expect you to know that in a cantilever beam, with a tension would be on the top. Now that we know that concrete is strong in compression, which means that whereas it has or effectively no tensile strength. So what that means is that we need steel to act as the tensile member to provide that tensile strength. So if the tension or the steel is on the bottom, that means it's loaded in a typical manner, which means the answer is D. Okay. Most people went with that, I think, just because it looks familiar. I think if they'd asked for a cantilever beam, and Copeland is on record as saying that he loves cantilever beams, just be aware. Okay, so I think a lot of people would have got that one wrong. Okay, so we've got a question on Venturi, and what I wanted to talk about here is that in my notes on aircraft instruments, I have the two definitions. So Bernoulli's principle is as speed goes up, pressure goes down, and Venturi is as speed increases. Yeah, so speed increases as the diameter decreases. Velocity of the fluid increases as it flows through a narrow, as diameter decreases, while the pressure decreases. Okay, so what we're seeing here is they're talking about a Venturi, and if they're asking us to differentiate between Venturi and Bernoulli's principle, I think it's a very tough question because they have that relationship. But what we can see here is that as diameter decreases, our speed should go up. And the thing that people are familiar with is if you have a hose and you cover up half of the hose, the water shoots out further. Whereas what we're looking at is as the fluid speed of the fluid increases, pressure decreases. So because it's going to go faster, the pressure will go down, and that is Bernoulli's principle. The Coriolis effect, I think, is like a global phenomenon that happens at the equator. Pascal's principle is when we have sealed containers, so that's the big force, big area, and dynamic pressure. I'm not even sure what they mean by dynamic pressure. Okay, so, but I'm very conscious of time, so I'm not going to think about it. Okay, the table shows that, okay, the order that these things have been used. Stone, cast iron, alloy steel. Seems totally reasonable. Let's move on. I would say cast iron was first used. It's sort of one of the things that kicked off the first industrial revolution. So Abraham Darby building Iron Bridge in Coalbrookdale is kind of one of the first civil applications of cast iron. Alloy steels weren't used for several hundred years later. But I can see that and I can move on. If they'd asked me which one was used first, wrought iron or cast iron, which we're going to see questions on that very soon, I'd have much more trouble. Stainless steel is much more modern than stainless steel is used in the in the early 20th century, so 1900 something. Chrysler Building is the picture I have on the back of the wall for that. Which one is used first, timber or stone? Well, it's really tough. I would say that timber was used first, but you'll notice that none of these questions are comparing that. They want to make it easy enough for people to be able to figure out what's going on. Most people got that. Okay, 12. Winglets. Okay, so winglets, if you watch the real engineering video on winglets, basically the answer is vortices. That by reducing vortices, and if I was more prepared and willing to put more time into this video, I would get the real engineering video up. But you can look that up. It talks about how winglets reduce vortices. So I guess the example is when you pull a plug out of a bath, that creates a vortex. Vortex create a lot of drag. So by reducing vortices, by decreasing vortices, we're going to decrease drag. And that's, I think he makes the claim that it's the greatest, in terms of fuel efficiency, it's the greatest innovation in aviation history. So the question is between A and B. The thing is, it also increases lift by keeping more of the air traveling over the wing. It means that we're going to increase the lift due to the Bernoulli's principle over the wing. So the answer, pretty confident, is A. B. Increases. Sorry, increases. I had selected increases, but I would have colored in the wrong bubble. I'm glad I checked. Check your bubble sometimes. Okay. The diagram shows a seesaw being used by two children. One of the mass is 25 and 20. Okay. It has a corroded pivot mechanism that reduces its efficiency by 25%. Okay, so this is an interesting question. So how do we compare this? That okay. So this is a tough one, and I can see that this was pretty divisive for students. That when we are calculating mechanical advantage, what we'll typically look at is mechanical advantage equals load over effort, and that is what is shown in the formula sheet. Where is my formula sheet? It's on this one. Okay, mechanical advantage equals load over effort. Where do they say that? There we go, machines. Mechanical advantage equals load over effort. That would be great, and we could look at if we could take a crack at saying which one is load and which one's effort. And if we took 20 divided by 25, we would get an answer that is in the multiple choice. The problem is that they're telling us that we need to calculate efficiency. That is the problem, efficiency. So what we need to do is we need to rewrite this formula here. So what we need to say is mechanical advantage equals efficiency times velocity ratio. Funnily enough, we actually need that value a lot more than we need the alternative. Mechanical advantage equals efficiency times velocity ratio. That's what we need to do. Now, in this diagram, what is the velocity ratio? The velocity ratio is the distance traveled by the effort divided by the distance traveled by the load. When we're talking about that, well, we can use the radius, the comparative radiuses or radii of these to make that comparison. It's actually what we're really measuring the circumferences, but because they both divide, the pi is on top and bottom, we can divide that out. So what we have is 2 meters versus 2 meters. And when you have 2 meters versus 2 meters, the velocity ratio is 1. Right, so in this case, if we have a first order lever can have a mechanical advantage equal to 1, or less than 1, or above, or greater than 1. Second order levers, like wheelbarrows, have to give a mechanical advantage greater than 1. And third order levers, like fishing rods or tweezers, they have to give a mechanical advantage less than 1. Now in this case, we have a first order lever which could go either way. But because we're saying that the distances are the same, well, we're predicting that the mechanical advantage of this is 1. We're not actually getting any advantage. If the little kid wanted to be more effective, they could sit further back, or rather the big kid could sit further forward, and that would be what they could do to balance that out. But what they would be doing is changing that 2 meters, and that would be how they could change it. So what we're saying is if the velocity ratio is 1, and then we said that the efficiency has been reduced by 25, so effectively the efficiency is 75%, we know mechanical advantage equals 75% times 1, which is B. Now, I will say that is a tough question. About half the cohort got that right. So I can see that's a trap for people. Now, it's not my place to say what is a good question or a bad question. Questions that are in the HSC kind of by definition are the standard of what is in the HSC. That said, when I saw this question, I didn't like it. I thought it was very specific information, but then lots of things that we teach are very specific. I now make a point about talking about what compression rates we use. I use that, it's in my extension notes. I could probably even find that very quickly. If we go to telco, analog versus digital, and I talk about compression. And somewhere in here, I talk about MPG or MPEG-2. Okay, so the point is that we're using FM signals to transmit the audio, and we're using MP2 or MP4. Voice over IP is used for telephones. We're not transmitting luminescence under any circumstance. So this question, less than half people got it, so don't feel too bad if you didn't, and we can move on. We're up to 14. Okay, titanium is why is it preferable over steel when we're talking about landing wheels? Okay, titanium has a low density. It's relatively light per cubic centimeter. Or it's certainly lighter than steel per cubic centimeter. I am not going to look up the relative densities. I mean, whenever I say that, I always think, oh, here we go. .1, whereas steel is 7.8, I think. There we go, 7.85. That is actually knowledge I used to use for my career. Okay, so titanium is about 2/3 of the weight, or it has 2/3 of the density. It's a lower density, and it has relatively high strength. So, yeah, B. What we're really interested in is strength to weight ratios, how much steel we need to provide in order to be able to meet the needs of something. I was reading something about Amazon trucks the other day, and they're talking about using aluminium versus plastic in the roofs of delivery trucks, and the comments on Reddit were saying that for the amount of weight that you need to provide the same strength, plastic and aluminium are probably going to be about the same. Okay, so we have an anchor from 1790. This anchor is likely made from what? Okay, I did not like this question. I thought it was a tough question when I saw it, and I remember reading this paper when I went and collected the paper when the exam was running, and I thought, oh, this is a tough one. And I thought, okay, well, I was able to make a prediction. Now, the key thing here is you have to make a prediction. You can't leave the question and not come back to it. So you're better off putting something down, circling it, and then thinking about it and coming back. You might have inspiration in 2 hours when you've got more time. The thing to know here is, I'll tell you how I work this out. And Rochford, he has John Rochford is someone who writes a lot of papers. He's an engineering studies teacher who he sends out his answers to everyone usually the day before we start marking. And he gave a good explanation, but I had my own explanation beforehand. You can buy all of his answers. Rochford's textbook is available. Anyway, here's what I came up with. I thought, what do anchors do? And I don't like this because it requires you to understand something about things that we haven't explicitly taught in engineering. But I have to think, what do anchors do? Most people know that anchors stop boats from floating away. And we'll think, well, is that under tension or compression? You'll say, well, that's under tension. And if you think about, well, tension, you can't have cast iron in tension. Cast iron doesn't have a very good strength in tension, so cast iron is ruled out. We don't generally cast steel, and it's probably not going to be laminated silicon steel because that sounds like it's pretty modern. So if we're thinking about between cast iron and wrought iron, and we rule out cast iron, that leaves wrought iron. Yeah, that's an answer you can give. Moving on from that, the next thing is, we can see the grains have followed the shape of the object, which makes it look like it's been forged rather than cast. And if you're thinking forging, well, that helps you to say, well, it's probably been wrought iron rather than cast iron. Okay, now this question is quite tough. Let me just have a quick look. 16, 17. Yeah, half the people were able to take a guess at this one, whereas this one people answer badly. Okay, so what we're looking at here is at room temperature. If we were to conduct the process of rolling without applying any additional heat, what are we going? Well, like at room temperature, so 20 degrees or 25 degrees. If we roll lead at 20 degrees, is that considered to be hot or cold rolling? What defines something as being hot or cold rolling? Now, I would think this is beyond beyond what I would specifically consider to be HSC knowledge, but here it is, so therefore by definition it is HSC knowledge. Okay, the recrystallization temperature of lead is 0 degrees, which hot rolling is any rolling that takes place over the recrystallization temperature. And so because this is 20 degrees over the recrystallization temperature of lead, we can define 20 degrees as being hot enough for it to be cold, hot rolling. Whereas 25 degrees is considered cold rolling because we know the recrystallization temperature for steel is 723 degrees. Always love to prove myself wrong. Yeah, okay. Between 400 and 700 degrees. There you go. I'm surprised, but I'm gonna run with it. I would have thought it'd have to be into the eutectoid range, so over the austenite range, the lower critical temperature. But I'm going to move on. Okay, shock absorber. This I think is actually a pretty easy and relatively fair question. What this tests is how many significant digits that often, and I think this is a real big problem for chemistry students as well, so be mindful, chemistry students, that often people will write 90 millimeters as 0.9, or they'll write 30 milliliters as 0.3 rather than correctly writing it as 0.09 or 0.3. Now, the reason this is important is because we always use SI units unless we're using Greece units. We go together like megapascals and millimeters squared. There's no megapascals in this equation. There's no millimeters squared in this equation, so we're going to be using this. So the distance, what we're looking at is, what is the energy? So we know energy is Fs. This particular year, I'm able to use I have a student who has the initials Fs. So I like to think about when you work out, you get sweaty. I can't think of what the F could be, some sort of adjective for F. But so if we say work equals Fs, so the force they've given, the force they've said is 400, and the displacement is 0.03. So if we go with 0.03 times, what was the force? 400. We're getting 12 joules. And I think that some people, you know, the the units is what gets some people in trouble, because only 50% of people got that. I should say the lead one, less than half of the people got that right. Okay, now, again, a question that was not answered well, and I'm surprised that it was not answered well, because I think this is a great question. But this has kind of been one of my things, so I can understand that, you know, maybe why people don't get it. Okay, so first of all, A is ridiculous and B is ridiculous. So why is B ridiculous? Okay, we'll talk about why B is ridiculous. B and D are both, excuse me, they're both wrong because the Australian standard effectively says that we should not. So this stiffener, right? It doesn't run for the full thickness, and if we section it as in the same using the same hatching, the manufacturer might think that that thing goes the entire thickness of the object, and if they do that, well, that's going to be misleading. So what we do in the HSE, we don't section stiffness. So we'll quickly go to my notes on this. I should have had them ready, but I don't. So if we go to, I had recently posted my drawing stuff again. I'll go to my year 11s. Graphics, AutoCAD, Advanced Orthogonal Rules. Okay, so what do I say here? Don't hatch thin sections. Page 85 of the Australian Standard. So let's have a look at that. Page 85 of the Australian Standard is... this. I don't actually have it numbered on the drawing, which is confusing. Okay, so this is page 85 of the Australian Standard. Says how for when relatively thin elements such as what we should do is we should rotate everything to be in line with the cutting plane. Everything should be rotated to be in to show all the interesting stuff. And what we should do is for thin sections like this web, what we're going to do is they can see that they've shown half spacing, but we're not going to do that because we're going to say that in the HSE, just don't do that like ever. Okay. So if I have this picture and I also have this picture, right? So here we have a very similar looking shape and we can see that we've moved our section line through all of the interesting stuff. Even though we've got 3 holes and 3 stiffeners, what we do is we rotate it so it looks like there's 2 holes and 2 stiffeners and we show them symmetrically. We don't do this. And the reason for that is it's just way harder to draw and it's very confusing for the manufacturer. Remember that the manufacturer has access to the top view. They can see that things are radially spaced. We call this PCD, pitch circle diameter, or pitch circle radius. The idea is that even if they just show a sectional front view, just rotate all of the interesting stuff to be in line. So that is what we're doing. The 2021 paper, it had a question which did exactly that, where it had 3 stiffeners and 5 holes. It expects you to show 2 stiffeners and 2 holes in the section. Okay, so that's why these holes are shown here and not close. So if we look at this picture here, we can see, well, the hole should be actually down here, but we've rotated them to be on the sides. And the reason we've rotated them to be on the sides is because we're using a pitch circle diameter. So that's why we're showing the holes running through. Now, so we don't show this. I think that it would be reasonable if we showed hatching every second. That would comply with the Australian Standard, but we just don't do that in the HSE like ever. Okay, so with that we can move on. C is the correct answer. And yeah, monkeys pressing buttons randomly would have done as well as the cohort doing that question. Okay, this question I think is pretty difficult. I think this is much more difficult than the other one. And I've had students come and ask me this week about this question. And to them I said, hey, the guy from Eureka Engineering, who I've spoken to and seems pretty on top of things, he has written a textbook, which I recommend. What he says is, first of all, to calculate the true or so first of all, we've given the engineering stress. The engineering stress is what engineers use, and that's when we have the area equal to the initial area, which was the initial area is 100 millimeters squared. Why do we do that? Because engineers are lazy. They don't want to keep measuring the diameters all the time. I do have some students say, all I can remember is that engineers are lazy. And I'm like, well, okay, you have to go that extra step and say, what does that mean? It means that we just don't want to measure the diameters all the time. But if we want to find the truth, we have to find the area at the point of failure. Okay, or at any point in time. And so what he said is, well, okay, if we calculate we've got the engineering stress and we have the engineering area, the original area, that means the force must be 15,000 newtons. And then if we go back to using the true stress, we can say that the 1500 divided by 90, 15,000 divided by 90 gives 176. It's also worth pointing out, it's going to be a number bigger than 150. The true stress is always bigger. I think it's fair to say that true stress is bigger. I'm just going to quickly look for something. Look, can I pause? I can pause the recording. Okay, hopefully the recording paused at that point. Sorry for the waste of time before that. Okay, so here's the picture. So we have, this is a guy saying you can't handle the truth, but I've made it, you can't handle the true stress. Blue is true, red is engineering stress. blue to the sky, so blue goes high. So that can help us to, so if we look at these answers here, I mean, you can almost just take C as a punt anyway. Okay, so that's 20, but yeah, Ali has a video, Eureka Engineering has a video on how to do that. Okay, unfortunately I don't have the picture, but I don't think it matters here. All we need to know is that there's toughened glass. Outline the advantages of using toughened glass for a belt bus shelter. I would say that toughened glass is going to be more resistant to impact than plate glass, and if it does shatter, it's going to shatter into safe particles. I think that's pretty reasonable. It's outline. So outline, I would say, my experience is that outline is 2 good answers, 3 bad answers, or 1 answer that's explained really well. So if alternatively, if you said that because toughened glass is produced by using jets of cold water to create areas of compression in the outer layers of the glass, that and this increases its resistance to impact compared to plate glass, I would give that 3 marks. That's my experience. But if someone said, on the other hand, it's more resistant to impact, and when it does shatter, it's going to shatter into safer shards. The fact that I'm saying safer shards already gives me the effect, or it shatters into shards which are less dangerous than jagged plate glass. That would be all of that's good answers. Okay, we can start clicking into answers here. So we have properties of toughened glass, high flexible strength, breaks in the shards, strong edge strength, which resists chipping during insulation and transport, which are good answers. I didn't know that, so always good to read these things. Okay, a laminated timber beam is used, apart from cost and aesthetics, justify why laminated timber is selected for this structure. So what we can say is that they can be made into complex shapes. They can be made into very long lengths. Also, they're free from defects because of, we can cut out the knot holes and defects in the timber when we're creating these lengths. What did they say? They talked about fire resistance. They also said a better strength to weight ratio than steel. So, yeah, they said designed, made into any size or shape, resistant to chemical attack. So there we go. Describe the testing procedure that would be used. So what they want is a describe. So we're talking about features. So that's what we're circling. Describe the testing underline procedure of the laminated beam. Support underline, or maybe that's a box, I don't know. Your answer with a labeled sketch. So labeled sketch is critical. So of this 4 marks, 2 marks is for the words, 2 marks is for the sketch, 1 mark is for the picture, the other mark is for the words. That's really key, that whenever they ask for a labeled sketch, it's imperative that you do that. Now, your picture doesn't need to look anything like this at all. If you showed, where was that thing in bending that I had earlier? Electro boom, we've done that. We're done with this. Yep, that would be fine. Okay, if you show this would be perfect, right? So what we can see here, this is a transverse beam test. So transverse beam test, we show 2 reactions and a load that's applied. We're going to measure its deflection. And so actually when they grade pine, this is what they do, is they have a roller that presses down and measures the deflection, and paint is sprayed on there to tell you the strength of the pine. So mechanically graded pine, MGP pine, is graded in that way. Okay, so where are we back? Yeah, so you need to have load, test piece, supports. Yeah, I mean, they're not asking for much. Okay, transverse beam test, you get 1 mark for identifying, I would say. And a beam is subjected to a single point. Yeah, something like that. Okay, nothing too fancy. You can read that. I've lost what I'm doing. Okay. Okay. Calculate the bending stress in the beam. Okay, so we've done lots of these questions. I don't know if I've answered this one on my YouTube channel yet, but it's possible. It's not particularly hard, right? So let's look at we have a formula sheet. So let's go to the formula sheet. We can see bending stress equals my over I. So M is the maximum bending moment, Y is the distance from the neutral axis to the extreme fiber, and the I is the second moment of area, also known as the moment of inertia. So let's go back to the questions. Okay, so first of all, what we need to do is, what is the maximum bending moment? They've told us that, 17 kilonewton meters, excellent. Then Y, what is the Y value? The Y value, just one other thing, because I wouldn't have said this except for the fact they've got a picture. The great thing about, well, not great thing, a glue lamb, another thing that you get is you can put the grain top to bottom, so that way it also helps to increase the strength of the timber, so that timber when it dries will always naturally bend based on the growth rings, and by putting it top to bottom, it means that you're not going to get warping as much. It helps to neutralize the warping. Okay. So Y is the distance from the neutral axis to the extreme fiber. What is the neutral axis? Well, if we go back to that transverse beam testing, we can see here that we have this line here that's neither in, so the top is in compression, the bottom is in tension, but in the middle, right, we can see the compression goes down, 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 and eventually it starts going to tension, tension, tension. But in the middle, it's neither in tension nor compression. We call that the neutral axis. This line here is under no stress. It's under no bending stress. It's not under compression or in tension. It's just neutral. The distance from that axis, from that line, to the atoms or the fibers that are under maximum tension or maximum compression are what we should use. Now, typically, if we're not sure which one to use, we should use the bigger of those two values. Will give us the lower number, which is the safer number. Right, so I always say big Y is critical, and there's a video of me somewhere doing a big Y. But if we have symmetrical sections, it doesn't matter. We just take the neutral axis is halfway, or it's half the depth of the beam. So Y equals 250 divided by 2. So we've got M, we've got Y, and then we're dividing by the second moment of area, also known as the moment of inertia, and you'll notice one of the things that I disagree with Copeland is that he has a tendency to use meters to the power of 4. And this is, I think, the only question, and maybe there's been a question more than 10 years ago, but very rarely is there a question with m to the power of 4. I hope that we never have another one before again. Why do I say that? Because if we look up a beam, we were talking at lunch about girders, and I was saying how the biggest beam you can buy is the UB610. And then after that, you have to weld up girders. And when you look at the information for these things, they will tell you the moment of inertia in millimeters to the power of 4. I have a book at the Steel Guide for Australia. I don't know if I can find Steel Guide. I have no idea what it's called. It's a red book. My copy is a red book. Anyway, if you buy this, it will give you these things, and it will just say 10 to the 6 millimeters to the power of 4, always. But in this case, they've given us, now I sung the song before, we go together like megapascals and millimeters squared. They haven't given us millimeters here, they've given us meters. And it's very, very hard to convert this into millimeters squared, so we don't. We just use whatever units they've given us. So if they've given us meters to the power of 4, we're going to use meters to the power of 4. So what is our formula going to look like? It's going to look like 17,000, not 17 million. Normally we do 10 to the 6, but not here. 17,000, because we're going to keep it, we're going to convert the kilonewtons to newtons, but we're going to keep the meters. And we're going to multiply that by 0.25, not 250. The reason why we're using that is because we're being consistent. We're keeping everything in meters. So let's have a look. We're going to say 1.25, which is 250 divided by 2, times 17,000 divided by 117 times 10 to the negative 6 gives us, now that will give us an answer in pascals, right? So that'll give us an answer of 18,200,000 and something. And they've skipped a step and they've given us that answer. To prove that, I'm going to type it in. 0.125 times 17,000, oh, that's not 17. 17,000 divided by 0.123. Okay, and that gives us an answer of 18.2 pascals, 2 million pascals. Okay, I close it quickly because I'm not using my regular calculator. Okay, where I can just use expanded or scientific notation. Okay, an engineer would need to take into account the following. Let's look at the question first. Oh, okay. I had an opportunity to speak to HSC markers about this question. So, outline the responsibilities of an engineer when placing a tower within a local community. There's lots of answers you can give. I can see that some people might look at this and just be stumped, right? Like a deer in a headlight and just think, I don't know what to write here. So what my answer is, write something. Think about the fact that it's only question A, so the markers may or may not be more generous. Think about the marks. They're saying 3 marks. Outline is very nebulous. When we look at the HSC keywords, outline is the most nebulous one. Keywords. Okay, outline is sketch in general terms, indicate the main features of. As far as I'm concerned, write 3 sentences or write 3 lines. Outline the responsibility of the engineer when placing the tower within a local community. So I would say that you could probably write 3 bad answers, 2 good answers, or 1 excellent answer. I generally would rather see 2 good answers, but I'm sure it's possible. Like when we talked about the toughened glass, if you've given a lot of detail, in this particular case, I just feel as though it's a broad question, so I'd rather see broad answers. Okay, outline the responsibility the engineer has when placing the tower within a local community. First thing I would say is safety. So they need to ensure that the tower is placed in a safe location, ensuring that the wall that's being constructed, that the traffic isn't disrupted, and if when the traffic is disrupted, that appropriate safety precautions are taken to ensure that pedestrians can walk safely to their destination, that their traffic isn't driving past each other without some sort of protection. I've gone way past that, right? I could just say it needs to be put in a safe spot. Another thing you could, if you want to elaborate on that particular point, is you could say things like you need to ensure that people can't accidentally enter the site, so that little kids don't walk into a hole and spear themselves on rebar, which has happened unfortunately. Another thing I would consider is the suitability of the site. So we need to ensure that it's in a site that gets good coverage. So it need to be up high. It might be that we want to have the towers far away from we don't want to disrupt other businesses. We might want to also consider things like the environment, right? So I always think about, when you're writing an essay, always think about economics, social impact, and the environment. So you might want to talk about economics, but just quickly to say the environment, you might want to say, well, if there are endangered trees, we might relocate it somewhere else. In terms of the social impact, we want to make sure we put it somewhere where it actually is going to work. Okay. Explain why they have put the transmitters where they have on the diagram. The big thing here, I would say, is that, well, okay, it's two main points. The first point is that it needs to be pointed at the direction of where the local population is. So you don't want to be pointing it out to the national park. You want to be pointing it towards where the community is. The second thing is that you want to separate them so that way it reduces the likelihood of interruptions, or interference from one signal to another. Let's have a look at, so they've talked about community, making sure up high to minimize dead spots, visual pollution so it doesn't look ugly, maintenance is good as well. Okay, so here it needs line of sight to the transmitter, and we want to minimize interference. Here we can say, I would say that would be an example of 2 very good answers rather than 3 poor answers. Explains why the repeater is positioned. Yeah, okay. It does it say explain? It does. So explain means cause and effect. So you do need to provide, make sure that you're saying it needs to be there so that, or because it is placed there. It needs to be there because it needs to have line of sight to the transmitters. Okay, now this question, as far as trusses go, I think it's fair to say this is probably the hardest truss we've seen. It's 6 marks, which is rare to have a 6-mark question. And what are we going to do? Well, so first of all, we have to find the reactions. I'm kind of past going through reactions on these things at the moment. If you're not sure what I mean, well, I have a video where I have gone through this, where I work out the reactions. Where I work out the reactions on the board, and you can watch that here. The next thing is, once you've found the reaction, so reaction A is 14.3. Once you've found reaction A, they want us to then find reaction N. Now, the important thing to note is that reaction A is a roller. If it's a roller, it means the reaction A can only have a vertical component. There's no horizontal component side to side. Now, if that's the case, it means that AC cannot have any value in it whatsoever. AC must be a zero force member, because if there's any horizontal component here, AC can't match it. It can't. There can't be any value here, because if this has 1 Newton to the left, there's nothing that can push back. N can't push back, and the reaction can't push back. So AC has to be a zero force member. What that means is that we know that in the sum of the forces vertically, RA has to be the same as RN, and that's shown in this diagram here. If we say that AC is a redundant member, therefore we know that AB, the vertical component of AB, has to match the vertical component of RA, which is 14.3. Now, in order to do that, because RA is pushing up, RN will be pushing down. It will be pushing into the node, and if it's pushing into the node, it's in compression. So you can just write compression by observation. Okay, then it asks for M. Now, to calculate M, again, I'm not going to click on my video again, but the idea is that we're going to need a cutting plane. And so I explained that the cutting plane is going to be here. We need something that cuts through M. Now, the extreme version is if we went this way, we'd cut through 1, 2, 3, 4, 5, 6. That would be ridiculous. We can only cut through 3 members. So 1, 2, 3. If we cut through 3 members, we're going to have 2 unknowns. Our 2 destructors are going to be dB and EC. So how do we get rid of them? Well, we look at dB and EC and we say, do they meet up? And they do meet up. They meet up at H. So we're going to take sum of the moments about H. Boom, you've got a mark. If you wrote sum of the moments about H, you get a mark. If you had shown the cutting plane, you're probably going to get a mark. If you do both, you're probably going to get 2 marks. What are we going to do next? The problem is, it's very easy for us to figure out the distance of the forces. So when we cut, we're going to cut above the line. So I'm going to just go into here. So here we have Aiden G. I don't remember, it does say his name at the end. I imagine he's a teacher. I don't know this person personally, but I just saw this on here. But it's a good diagram. So he's showing he's cutting this line here. We're only going to take the top. Why are we going to take the top? Well, if we take the top, we can't be wrong. We don't need to calculate reaction C, which is nice for us. That speeds us up. We only have 2 external forces, the 7 and the, you have 3, 7, 13, and 12. I find that going around clockwise helps me and prevents me from missing out on forces. If you miss out on forces, you might still get full marks on this. I will say that I don't think this question was answered particularly well. Actually, we'll quickly talk about that. We'll come back in a second. Okay, so what are we looking at? Okay, so we've got these 3 forces, but the thing that makes this difficult is we need to calculate the perpendicular distance of E. Now, what you could do, I guess, is you could calculate the vertical component and the horizontal component of E, but I think you end up with a simultaneous equation, and I wouldn't want to do that. That seems like too much work. So what we're going to, it's important to remember we can ignore BD and EC. What we're going to do is we're going to calculate the perpendicular distance to E. And if we look at the answers here, they're going to show us what that looks like. They're going to show us this value here. Now, you can use your trigonometry to do this. And ordinarily, I would just say, if you have a question like this, just draw the D and just scale it. Just draw that distance and just scale it. Just draw that line out, get your set square out, keep drawing, extend BD, which is what we're calling M, extend this out here, and then just run your set square along until it touches H, and then draw your perpendicular line. And then measure it to scale. We've got 6. Oh, but it says not to scale. Now, I have looked at this question a little bit, and I knew that it said not to scale. Now, the question is, will the HSC markers mark you down if you've drawn it to scale? Well, I'll just say I think you'd be very unlucky if that was the case. Now, the question is, how badly is this out of scale? I don't think it is. I actually think the thing is drawn to scale. And you're allowed to draw your diagram to scale. You're allowed to draw this up. If you think that you can't figure out the trigonometry, and this is relatively hard trigonometry, it's a two-step process. You need to do Pythagoras' theorem and then calculator, which they do work out in the answers, and I've done my video here, so they've got Pythagoras' theorem and then they've calculated here. But I think markers are just going to look and see, is there a value for D? And if let's say your value for D was 11, right, which is out by a fair bit, I think probably still we're not going to lose more than 1 mark, and better to lose 1 mark than to get no marks. Anyway, so once you do that, the question sort of falls together. I've got videos talking about this. I don't need to go through it here. Okay, let's keep going. Okay, so this scooter question is not difficult, but it's not the sort of thing we've seen a lot of. So this might be a good thing for my next half yearly. Okay, so we've got initial height of 2 meters, and we're going to go some additional height here. Now, to work this out, the formula sheet, what does it say? The formula sheet can be expressed in different ways, but at the moment it writes work equals Fs, which equals delta P plus delta Ke. Another way of saying that is work equals Pe, delta Pe plus delta Ke plus Fs. I think that's a good way of approaching it. Now, I'm pretty sure this thing is going to be frictionless. Let's have a look. Assume no loss of energy. Okay, so what is our initial height versus, and so our initial height is, do they tell us the height? That the weight is 55 kilograms. So we're going to have the potential energy just from simply being in occupying space is 55 times 2 times 9.8, which we're going to call 20. 2 times 9.8, but it's close enough to 20 because we use 10 for gravity in this course. We're allowed to do that. And then we're going to have half mv squared. So we're going to have 1.5 times 55 squared. I'm not interested in typing that into a calculator, but we're going to get a number. And then what we can do is we can divide that number by 20, and that is going to give us our new h. Let's have a look. So we get this number. Oh, it's a simultaneous equation because they do have h. Yeah, okay. So I would have done it this side. So we said they've actually taken the m's out, which is great. That's a very clever move. I wouldn't have done that. So they've said that everything can divide by m, right? We can put brackets and then take the m out. That's great. Very clever. And what we can say is that I said, so half times m times 3 meters per second. I think I said 55. Whoops. Anyway, that makes way more sense. I wrote on someone else's trial paper that 55 meters per second is incredibly fast. Like, there's nowhere in Australia, I think on the Autobahn, 55 meters per second is going to get you ticketed. Anyway, but 3 meters per second, that's totally reasonable. Okay, so half times 9, which is 4.5, plus 20. Yeah, which is that, and then we're going to divide by that, and we get the answer of 0.5 meters. Okay, moving on. Ooh, okay, battery questions. Battery questions are something you used to really only see in trial exams. And trial exams, they have a different standard of difficulty to our papers. So what we're going to look at, is this the question we're looking at? No. So this is there has been another one since in the 2021 paper where they've talked about batteries and amp hours. I personally don't like it. I don't think it's explicitly in the syllabus, and I think that, I mean, they do have power sources. Maybe that's where how they get you. Yeah, power source. I'm going to write a little note. That's where I can put in my notes for year 11, because we do talk about power sources. The problem is our syllabus is not as explicit as it could be. So really, we rely on past HSC papers to know what to expect. Okay, so in this question, what we're going to say is 12 volts with 18 amp hours. We're going to use 1 watt hour equals 360 joules. They helped us out there. In the answers, they explain that 1 watt equals 1 joule per second. So in an hour, there's 3,600 seconds. So 1 watt hour equals 3,600 joules. Now, what they're looking at is they also give us power equals volts times current, even though they like to use EMF on the formula sheet. the tricky sons of guns. Where do they show? So in the formula sheet, they say power. They don't even. So they have E for electromotive force equals IR. I like to think of P equals IE, which is pi, or P equals VI. And if you replace the V with IR, we get P equals IIR. So IIR we can say is I squared R. And that's why they give you the formula here, because they don't want you to calculate that. So they're saying 12 volts. P equals IV. And so I is 18, 12 is V. So P is going to be 12 times 18, which I can't do in my head, to 16. We're assuming it's running for 1 hour. It's nice of them. So 216, and then we're just going to convert it by that. Pretty easy. I said I was going to go back and just talk about how hard these questions, relatively speaking, were. B23B. Less than half. Okay, I'm just going to point out the ones. I will say pretty much everything. We're talking about half the cohort getting pretty much everything, except 22A, which most people got. 22A was pretty popular. 22A. Oh, okay. Yep. Hey, I wonder who was generous when they were marking that thing. Okay. So all of this other stuff was marked really badly. 21B, apart from cost and aesthetics, no one knew glue lam. 21C, nobody knew how to test glue lam with transverse tests. And then 22C, oh yeah, okay, that was a hard, I mean, trusses are never answered well. But you know, it was particularly hard truss, and yeah, I had an inkling that that would be the case. You don't get to see the spread of marks, but I would, like I said, I am able to talk to HSC markers, and I get the impression that very few people got that right. Like very few people got 6 out of 6 at all. Okay, so as we keep going down, 23C, yeah, we're still in this sort of, you know, half or floating around half range. 23D, same thing. Okay, so we've got this beam and we're saying that it's deflecting too much. When we're on our scooter, we're bouncing around and we don't like that. So how do we make it stiffer? Well, we should be pretty familiar, especially in the older papers, like 10 years ago, they used to love these sorts of questions. And if you do civil engineering, you'll see these a lot where, oh, okay, I skipped a question, sorry. I'm going to continue with this and I'll come back. The idea that by making it more like an I-beam, by creating these 4 I-beams, we're going to increase our stiffness, right? We're going to increase our bending strength and we're going to increase our stiffness. It looks like I skipped a question. We'll come back. And okay, so this is an interesting question. I haven't really seen a question like this before, and it really is like you can put all the pieces together and it just works. But the idea is, I watched a kids documentary where they said that they were able to calculate the weight of a car by just measuring the area of the tires connected to the ground and also measuring the tire pressure of the tires. So what they said is that for the area of contact between each of the 2 tires is 1,200 millimeters squared, and the tire pressure is 300 kilopascals. And we've got the weight of a rider. Let's figure out the mass of the scooter. Okay, so we know stress equals force over area. So force equals stress times area. Now, we want to use everything in, we go together like megapascals and millimeters squared. So me personally, because I don't like to convert anything squared, I find converting stuff that's squared difficult and problematic. I'm going to instead convert this to megapascals. So I'm going to say 0.3 megapascals. So tire pressure is usually measured in kilopascals, whereas everything else we do in the subject is in megapascals. Soil pressure is also in kilopascals. So me personally, I would say 0.3, but you notice that they've done it in pascals. Good for them. They're smarter than me. Anyway, the point is we're going to get the same answer. Our tire pressure is going to be, they've just crossed out those orders of magnitude, and then they've crossed out some numbers, and they've got 36 newtons per tire, which gives us 720 newtons total. And then we take away the weight of the rider. Do they give us the weight of the rider in newtons? Great. What physicists they are. Which gives us 70 newtons left over, so that's 7 kilograms. It's slightly more, but we're allowed to use gravity as 10 in our subject. Okay, so yeah, by having these stiffness go down further, even if the stiffness didn't go all the way down, I would still say that was better, but it probably is better to have the stiffness go all the way down. Okay, imagine the aeroplane. This is an interesting question. I'm going to bet that this one wasn't answered well, because... better than I thought. Oh, okay, so I'm jumping ahead. Compare the use of composite materials with the use of metals in the manufacture of a beam. Okay. So we've got compare. I don't know if I still have the glossary of keywords. I do. Okay. Compare. Show how things are similar or different. Okay, so we can say that although early aircraft was typically made out of aluminium as it became more readily available, these days, modern commercial aircraft is much more likely to be made of CFRP, so carbon fiber reinforced polymers. You're allowed to write the abbreviation, or composite materials. Composite materials such as CFRP or FMLs, which is fiber metal laminates such as glare. Sorry?
It says metal in the question.
Yeah, we're comparing the composites with metals. Yeah. So I've said aluminium was typically used. So the Wright brothers, they used aluminium in their jet engines to reduce their weight. We can say, so what is similar about them? In both of both metals and composites, high strength to weight ratios or low density materials are definitely preferable, because by reducing weight, we reduce the cost of fuel, and it makes the flights, makes us more cost efficient. Also, for both aluminium and composites such as CFRP, corrosion resistance is an important factor. However, an advantage of CFRP is they have increased fatigue resistance. Now, if you wanted to watch more, you could. Real Engineering has a video where he talks about why are the Dreamliner's windows so big, and he talks about how because of the changes in pressure, air pressure, it means that the fuselage of the plane actually expands and contracts a lot. And the point of weakness where the failure is likely to be is in windows, which is why windows have a rounded shape and why they tended to be smaller. Whereas as we use carbon fiber, we know they have much better fatigue resistance, which is why we can have bigger windows on the Dreamliner. The Dreamliner has both a passenger comfort safety. The big windows have both a passenger comfort and a safety feature. Okay, so that's a pretty extensive answer. Let's see what they wrote. Okay, composites are lighter, required specialized equipment such as an autoclave. Autoclaves, even a small autoclave, is like $80,000 to manufacture CF or epoxy composite beams. Metals are heavier, can be fabricated, so we can weld them, right, with the TIG welding is an advantage. Look, that'll do. You can read their answer. It's not a bad answer. I'm pretty happy with what I wrote, and I think they were pretty generous with the marks on that one. Okay, normalized high tensile steel has been used for the manufacture of the wing. Draw unlabeled normalized steel and in annealed steel. So what we're going to look at is, if they said high tensile steel. So high tensile steel, if you drew 100% perlite, that would be fine. I would say we want to draw anything up to 100% perlite. You probably don't want to be showing hyper-eutectoid with cementite layers. Anything up to that is fine. I've looked at the answer, so I think they've drawn about 50%. We'll have a look in a second. Now, it's important to note that the normalized steel is going to have smaller grains and the annealed is going to have bigger grains. Now, I usually draw, yeah, that looks good. I normally draw like 5 or 6 grains for annealed, and I try and draw about 10 or 12 grains for normalized, or maybe 16 grains, I don't know. The point is, if you notice you started drawing really tiny grains and you're like, oh man, I'm wasting my time drawing little grains, you don't have to draw the whole circle. I mean, I've been told that. I've never marked one of these questions, but anyway. So you can see here, now I would think for high carbon steel, we could actually go to everything being perlite and no ferrite grains. But Note that they're small and equiaxed for normalized, and they're large and equiaxed for annealed. They have labeled ferrite and pearlite. That's what we're looking at. We've talked about before how really important that for these 2 marks, one is for drawing, one is for labeling. I can't stress that enough. Okay, explain how the microstructure produced by normalizing high tensile steel improves the suitability of this application. Okay, I've spoken to HSC markers on not about this specific question, but on questions very similar about normalizing. And I will tell you that it breaks my heart to hear that if you write the word stronger, normalized steel is stronger than annealed steel, they will not give you a mark. It breaks my heart that that is the case. I'm not in charge of the HSC. I might be one day, and when I am, I tell you, I'm going to really try and make that change, that I think the word stronger is acceptable. In the HSC, they have cancelled Kanye. You cannot say stronger. Instead, you need to say it has more tensile strength than annealed steel, right? So much so that I'm going to pause for a second. Okay, so some of you might be familiar with our heat treatment means. So we've got annealing, we heat to 100% austenite, we cool slowly in a furnace. Result is we have to say aloha anneal. Aloha anneal, low stress, soft, big equiax grains. Pineapple tins, they are tough so that when you drop them, they dent, they don't break. Normalizing, we cool in steel air and it's harder. It's not stronger. We cancel Kanye because he just, it's unacceptable behavior. More tensile strength than annealing. Okay, so yeah, explain how so I can tell you, because I've seen similar questions to this, that for 2 marks, explain, you have to talk about the change in material properties, one change in material property and one change in like microstructure. So what you can say, it says explicitly, explain how the microstructure, I really should include this question. 1924, what is this? Okay, so we can say because it has smaller equiax grains, it has a higher tensile strength than annealed steel. That would be fine. Okay, so next question, with these planes, we're looking at the loading, and they say that the lift, the center of lift is shown, we're treating it as a point load, because in the HSC, the syllabus says we can't have calculations to do with UDLs. So we're treating the lift as being a single point load in the middle of, not the middle of the wing, at 7.5 from the, is located 7.5 from the center line of the plane. So that's like here, right? So what we're going to have is, and this is where I really wish I'd drawn my own diagram, but I haven't, and I'm not going to do it now. We're going to have a diagram that's going to go up. How much is it going to go up? Well, what is the total weight of the plane? The total weight of the plane is 600. So we're going to have 300 go up. Then we're going to go down. We're going to go across. We're going to go down 30. Then we're going to go across. Then we're going to go down 540. Then we're going to go across. And we're going to go down 30. And then we're going to go across. And then we're going to go up 700. That will be what our free body diagram will look like. So let's draw that again. Going to go up 300, across, down a little bit, across, down a lot, across, down a little bit, across, up a lot. And then, so yeah, shear force diagram is going to show that, what I just mentioned. And then the bending moment diagram, we're going to calculate the area. So it's starting at 0, at 7.5, we're going to go up a fair bit. And then we're going to go across a little bit, and then we're going to go down and down. Let's have a look at their answers, and we'll explain it a bit more. Okay, there are multiple ways of calculating. So here we can see that we've gone up 300, we've gone across, down 30, across, down 540, across, down 30, across, up 300. Now, I personally don't like the arrows being shown that way, but I can understand it. It's fine. Now, the thing to notice is I thought it would be a steeper thing, a little bit more flattened, but it's fine. I didn't do the calculation. How do you work this out? Well, what you do is you can work out that this is 1.5 meters away, right? This is 1.5 meters away from the 6 meters. Does that make sense? Yep. Okay, good. So what we're saying is that this is 300 times 1.5. And we get 300 times 1.5. 300 times 1.5 equals 450, right? And that gives us our number here, 450. And then what we're going to do is we're going to take this block, and this block is 6 times 270. 6 times 270, right? And that's this big number. But that is not all. No, that is not all. It's plus that number. So we're going to go plus 450. Oh, that's not right. Plus 450 gives us 2070. A lot of people don't add those two numbers. Remember, this is plus. Then what we're going to do is we're going to go down. This block is a negative block. So we're doing minus 270 times 6, right? And when we get that number, we're going to get, oh, wouldn't you know it, back to 450. And then we're going to have this area. And when we take this area, it's also negative, which gets us back to 0. Right, brings us back to 0. Okay, so we actually, even though it doesn't look like it, we actually start at 0 and end in 0 for both our shear force and bending moment diagrams. If they don't start and end at 0, you've done something wrong. And that's where I actually really like to draw an arrow up, 300 up, down, 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 up. And if it doesn't end at 0, you've done something wrong. Remember that these are the area under the curve. Anyone who's done calculus at this point should really understand that this is area under the curve. That's the integral, right? All right, this is the integral of that one. Okay, you would tell me if I was wrong on the internet. Okay, so modern racing yachts, I don't have a picture, but that's okay. This picture is plenty good. How can engineers understand the effects of drag to improve the design of racing hulls? Now, I will point out that this is not the first time they've had a question on hydrofoils. Today at lunch, another Today at Lunch story, I was watching people with these things, and you can see why Magic the Gathering cards I'm looking at. Yeah, so it was that. Okay, here's that question. So we're looking at, so this picture that we're going to see here, these boards, they actually come out of the water because we generate enough lift that these things are going to come out of the water. And we have questions where we have a catamaran which also has a hydrofoil, and the idea is that by generating lift it is going to reduce the drag on the yacht. So you should be familiar with that, and this has happened enough times that, you know, there's probably not going to be one in the 2023 paper, but you know, there might be. So have a look. Okay, so how can engineers understand the effects of drag to improve the design of racing hulls? Okay, so they're talking about drag. They're not talking about generating lift here. What they're saying is by having smooth surfaces and an aerodynamic shape that reduces vortices, right, we can reduce drag, and even though it says how, that means we're looking for an explain, right? Explain how. So by having very smooth surfaces that reduce vortices and designs that reduce vortices, and you know, streamline the flow of the water around the vehicle, it means that we're going to reduce drag. Reducing drag increases the speed and makes the boat more competitive, right? So we've got an actual end goal. The end goal is, why do we care about the boat being fast? We care about the boat being fast because it's a race and we want to win, right? If it's not a race, it's because we want to save money. It's because we want to get people to their destination faster. Okay, so I think that's pretty good, but let's have a look at their answer. Minimize drag, increase thrust, polish surfaces, streamline shape, yep. Finite element analysis is where we use computers to simulate wind tunnels and that sort of stuff. And minimize weight through choosing, good answer. Yep, good answer. Reducing the weight reduces drag. Okay, so we're going to talk about these different materials, talk about why we'd use them. So Kevlar is used, or aramids. I like that they've even told us Keramid is, they've given us that to really help us out. Aramid fibers, also known as polyamides, have very, very high tensile strength. Right, that's the property. That's what it does. Complete the table by providing the property. It doesn't say explain the property. We just have to describe the property. Okay, that's fine for 3 marks. That's fine. CFRP, so carbon fiber reinforced polymer or epoxy composite. We can say that we've already talked before about good corrosion resistance and good fatigue resistance. So that's a property. Aluminium alloy, good strength to weight ratio, good corrosion resistance, or relatively, it has a passive oxide layer, which means it's less likely to corrode. It can also be TIG welded. So it doesn't say like a mechanical property as well, so just keep that in mind, right? We can talk about density or conductivity or anything. Okay, so high strength, high tensile strength, yeah. Carbon epoxy is also used because it's very, very smooth, can be molded into complex aerodynamic shapes. Excellent answer, that one. Okay. Okay, so we've got a CAD image. Why do we use CAD software? There's 3 reasons we use CAD software. The first one is sharing and storage, right? But I kind of think of that as the sharing answer. The second reason we use CAD is because it's editable. And the third reason we use CAD is because it can be integrated into CAM, right? So the first thing is because it's online, we can very easily send these files to stakeholders or colleagues who are working remotely. We can use 3D models to give a very good understanding of the shape. We can look at it and we can rotate it. We can turn it upside down. We can see how it fits in with the other things that it needs to connect into. And the client can just say, oh, I don't like that. That looks hideous. And we say, okay, don't worry, which brings us to our second point. We can very quickly edit the design. We can modify it for when we want to scale up. We can duplicate it. We can make changes quite easily. We don't have to rub out the hand drawings. The third major reason is that it can be incorporated into CAD software, into electronic software. So one of the things is, so like for large scale stuff, surveyors, I always talk about how this surveying information can be perfectly inputted into the drawing, so we can get down to the millimeter over the course of kilometers, and so it's an incredible range of scale that we can measure, and we can have that information available at our hands. Or at the same time, it can be plugged into a 3D printer, and the 3D printer can produce this material. That is an easy 3-mark question, and CAD questions are relatively common. So what do they say? Intricate components, visual image representation, so it's like sharing. We can print hard copies. We can do finite element analysis, so if we want to test it. It allows us to modify it. We can share it. And it doesn't talk about CAM, but I would say, well, this machine is almost certainly not going to be made by hand. It's almost certainly going to be made by a CNC machine or a 3D printer. Okay, so we have a board with a hydrofoil. I showed you that picture a second ago. I might still have it open. I do. Okay, so wait, no, it was not this one. It was this one. Okay, that's what the picture looks like. I don't know where I got that picture, but the hydrofoil of the board is used to lift the board out of the water, and I might have just got a board and just stuck it in there. I might have done that. That's possible. Anyway, it's fine. Explain why the hydrofoil can lift the board out of the water when it is traveling at high speeds. Okay, so this is just a general lift question, like a Bernoulli's lift question, which is exactly where I've got this thing from. I'm not going to go to my thing on lift. We're just going to say that water traveling faster over the top of the hydrofoil generates an area of lower pressure relative to the water below the hydrofoil. This difference in pressure creates lift. That'll do. Right, there's lots of other answers we can give. I had a student talk about the compressibility of water. I don't think that really comes into it. I haven't found any research. If you find research from an academic source that says that, I'm more than happy to take that on board. Okay, so yeah, water travels faster over the top. That creates an area of lower pressure relative to the water below. This difference in pressure generates lift, and that can lift the board out of the water. You can also talk about, so in 60 Symbols, Brady talks to some professor where they say, why does it happen? They say, well, it's a couple of things. There's actually more water that hits the bottom of the hydrofoil. It's also the fact that by changing the direction of the water, that means that we're going to have a conservation of energy, which means that, well, if the water's now going down, something else has to go up, and what's going to go up is the hydrofoil. Okay, with that said, we can move on. An interesting question here. Explain how mechanical energy from pedaling was used to make electricity. Basically, the idea of movements plus magnets equals electricity. You can't write that. I would only give, if I literally saw that in a HSC question, movements plus magnets equals electricity, I'd give you 1 mark. Let's say if you explained it a little bit more carefully and you said that the movement of the pedals turns a generator, and that generator reacts with a motor and creates electricity, I might give you 3 marks straight away for that. Okay, the thing we're looking for here is explain how. So, that's not bad. what we could say is because the movement of the pedal turns a generator, the generator will induce current into the coils of wire relative to the static magnetic fields. This electricity can be used to power the radio. I'm going to give that 3 marks. That's me coming up with on the fly. I think it's always a little bit harder because I'm not writing things down, but I can't go back and edit anything. The generator is made of a magnet and coil of wire. Good. Pedaling spins the magnet. Good. Generates magnetic induction. Yeah, that's fine. It is used to power the radio. As the generator increases, the voltage also increases. I don't think you need this last line. I think you would still get 3 marks without that. But that's good. Okay. I think you get 3 marks without magnetic induction. Now, this question, I think it's fair to say that markers felt as though this was a hard question. Not this part. This part's fine. But the next part was fine. The next part is hard. Now, that said, I haven't looked at how people have been answering questions recently. How far away are we down to 22C? 22C was not answered well. Oops. How far back is that? I think that was the truss. Yeah, so everything was fine till 24A. Bless you. 24A, we said, yeah, people did well. 24BI, yeah, I said, but no one does what bending well. (24BI), what's that one? Oh, okay. Yeah, no, that's unforgivable. You should be getting that one. People should be getting that one better. The bending 24. What is this one? 24D maybe. Sorry, 24C. 50-50. Yeah, I guess there had been one previously, so people had studied it. This one, yeah, again, there'd been one recently, so people had studied it. The Kevlar material, 25B. Yeah, no, people did well there. They're doing well there. 25D, yeah, they did well. Yep, everyone should have a good understanding of the generator was good. Okay, so this here's 50-50, and then the next two were like abysmal. Okay, so we've got an antenna, and we've got a fixed capacitor, a variable capacitor, we've got a tuning coil, we have a signal diode, and we have the headphones. Okay, so I have lots of stuff on demodulation, mostly as a result of this question, right? This question it inspired me to go and put more work into my demodulation stuff. Just point out that I have some stuff on heat treatment about forging and so different forging examples, welding examples. I probably should have a past welding question. Anyway, so what do we got? I was looking for that one. I was looking for the heat treatment. I was just terrified for a second. I'd maybe paused. Okay, so radio demodulation is where I've got these answers. And I've got some really good videos on Real Engineering talking about vacuum tube, how you can buy kit radios. I've got a video showing how these things are made. I have my video goes through these answers in more detail. I thought that I had Technology Connections. I really like his videos. Anyway, so you can buy these crystal radios, and I think that's the diode. I'm gonna, if I had to put money on it, I would say that I think that's the diode. And here we have our cat's whisker, which is how we dial in the radio station.
There you go.
This is some guy making it with very, very cheap components. I can't remember what he uses as the crystal, but as his diode. And then he has a more detailed explanation, which goes into exactly why these things work. We're not going to go into that lunch level. What we're going to say is the antenna collects the signal, right? The antenna, along with the tuning coil, allows us to receive the signal. The fixed capacitor smooths the signal. The variable capacitor allows us, with the tuning coil, to select the frequency of the radio station we want to listen to. The Earth provides a point for it. Without the Earth, there wouldn't be a flow of current, and we need the negative terminal for the current to flow through in order for the electricity to flow through the circuit. And then signal diode rectifies the circuit, removing half of the received AC signal. Okay, so that will make more sense when we go through it in the next part. Okay, so this is the signal that we initially get. We can see that's an AC signal, and the sound is actually this here. But in order to transmit it, what we do is we modulate it with the AM radio, so all of those little wavelengths. That's how we can send it very far using radio technology. And what we want to do is we want to turn this kind of symmetrical looking wave, we want to turn it instead to this line here. So the first thing we're going to do is we're going to remove the bottom half by using the diode at B. And now I don't actually think they use it I'm talking a little bit out of my subject area, like my specialty. I don't even think they use silicon diodes, because silicon diodes are too good. They have to have used slightly less good diodes, otherwise you won't get a flow of electricity. But that's what the videos tell me. Okay, and then so we remove the bottom half. We can just rub that part out, and then at C we go through the capacitor, and we said the capacitor smooths out the signal, and it takes it from being a whole bunch of little waves into one big wave. I can have a look at the answers and we'll see what they say. Okay, antenna picks up the signal, capacitor smooths out the signal, variable along with the coil detects the signal, earth acts as a negative pole, really simple answer, and signal diode only allows half the signal to flow through it, rectifying. Okay, here we have the original signal, and then we've just removed the bottom half, rectifying it, and then we've used the capacitor to smooth it, and that will give us our music or our talking, or whatever it is that we're transmitting, our SOS signal. Okay, this AM radio needs a speaker. Why speakers have high impedance? Why do they have high resistance? In order to produce sound of sufficient volume. The best way I can think to say this is that power equals I squared R, which means that if the resistance is low, the power will be low, and if the power is low, we won't be able to hear anything. That's the best answer I can give. I think that gives a how and why, right? If the resistance is low, then the power will be too low for us to hear anything. So by increasing the resistance, the power will be high. That's basically what they say here. If you watch the technology connections, which I'm worried I don't have in that video, he talks about how the vacuum tube is really important, because the vacuum tube and then later the transistor were what allowed us. So initially we had vacuum tube radios, and then we had transistor radios. And transistor radios, the role of the transistor is to amplify. So if you had a question, I mean, I've never seen this question, but if you said, explain the role of a diode in a crystal radio and a transistor in a transistor radio, you'd say that the diode is important to rectify the signal so that we can demodulate the signal. And the transistor is important because it serves as an amplifier so that we can play music through a speaker rather than listening through a headphone. Okay. Explain why detailed drawings are used in design and manufacture of these individual parts. Okay, so like drawings, there's lots of things we talked about here. Okay, so but the big things I'll say is by providing detailed drawings, sometimes I might talk about the Australian standard and saying by having a standard, it means that we can work more effectively. We're not going to have ambiguity. We're going to have fewer errors. So a lot of those things really apply here. By having detailed drawings, it allows the construction engineer to appropriately plan the work that needs to be done, to order the sufficient materials to be efficient. It also is going to ensure that there's less likely to be mistakes, and that if there are mistakes, that we can actually make we can determine who has made that mistake. By using the drawing. It's either been the designer or it's been the contractor, and in a world of litigation that's pretty important. Okay, lastly we have a fairly difficult, I think this is the last question, fairly difficult question. Yeah, there we go. Okay, I'll quickly go back to their answers and yeah, BI. So this question was answered badly. So yeah, the drawings very well answered. Probably is actually looks like the best non-multiple choice answer. So almost everyone got the why we use drawings question. Good work, everyone. BI was very low. So how do we answer this question? So I talked about this previously in my trial, so I'm not going to go into too much detail here. But there's a fairly detailed worked solution. The first thing we need to know is that it's in double shear. So if it's in double shear, we're effectively doubling the area. The second thing to notice is that it's we have a factor of safety of 5. So effectively, we're taking 1/5 of the allowable stress. Once we do that, it's really stress over area. But remember, when we're talking about bolt shear, we're talking about the cross-sectional area. And remember, we need to multiply by 2 because it's double shear. I think this is a formula really well worth remembering that although maths teachers will tell you pi r squared, that's just because if they don't teach kids pi r squared consistently, kids will get it wrong. I would tell you this because I taught year 8 last year and I had discussions about it. But for engineers, we almost never use r, ever. Like we're always given diameters. Like we can't really measure radiuses. We have tools that can measure diameters, like vernier calipers, but we don't actually have tools that can measure diameters. So everything is specified in terms of diameters. Pipes are in diameters. Bolts are in diameters. Everything that we given is in diameters. So that's why, especially if you plan on actually working in engineering, make the switch now. You'll be grateful that you did. But this formula here, even if you just write it down enough times, it just becomes familiar. D equals the square root of FA on pi. That really, just being familiar and like, oh yeah, that looks familiar. And I will say that as someone who writes this out and a couple of times a year, writing the D equals the square root of FA on pi, you want to get to the point where that looks familiar. And just so that way, I'm not saying you have to memorize it, but just you want it to be familiar. Anyway, when you do that, you'll get the answer of 6.8. You can't buy a bolt that's 6.8. So in order to be a good engineer, we're going to want more bolt, not less bolt. I think that makes sense. So we're going to go to 7 millimeters. And so 7 millimeters is the answer. If you wrote 6.8, I don't know. I didn't mark this question. I can't tell you whether or not you got that one right. Okay, the last question was a drawing question. Drawing questions typically aren't answered very well. This is only a 3-mark question. On average, people got a little bit more than 1.5. So I've looked at a lot of students. I make my students draw this drawing. I didn't mark this, but I've marked similar questions, so I have some sense of what is given and not. I don't think you would have lost any marks for not including that, funnily enough. I can't say that definitively. What I'll notice is that they didn't show the thread on these here. This is clearly shown as being threaded. So the HSC, I would say that I would want to see the thread, and I wouldn't care about this hole. I'm a believer that you don't show hidden detail in drawings that have sectioning, so I wouldn't have shown that. Either you show it as cut through, in which case you have a line and just easier to forget it. But really, they're not expecting very much. They just want you to show hatching, and they want you to show the holes, and they want you to show that there's a thing that goes here. If you did a different, if you did say 7 millimeters above and you drew this as 10, I don't think you'd lose marks. Anyway, so I know when I see these, and the thing you got to remember, even with a 3-mark or a 6-mark question, I really would urge you that always attempt, because in a 6-mark question, if you have attempted the drawing and you've made some attempt at it, you're going to get 1 mark. You're probably even going to get 2. In this case, you're going to get 1 mark just for drawing something. I mean, if you haven't drawn a smiley face, anything that you've drawn is going to probably get a mark. And part of it is just they want to see that you've even understood that you're drawing it from the top view. That's part of what they've... Did they ask for top view or did they ask for front view? I honestly don't know. Yeah, they asked you to draw a top view. So, I mean, there would have been students who drew a front view. And, okay, maybe if you've shown something, we'll try and give you a mark. But the big thing, I just tell anyone listening, but mostly to my students, please always attempt the drawings. I know that there are a lot of people who say drawings are too much effort, they're not worth enough marks to worth attempting. But you need to pick up the mark for trying. And with that, I'm going to say I hope that's been benefit and good luck.